thanks for having me again this year in this great user group. I am pleased to be again in Moscow and talking about technology, and it's the thing that I love most. And okay, so no videos. We are recording. That's a mess. I mean, I wanted to talk about you about nested things. So, I'm here to talk about very, very cool APIs that not everybody is already using, and so why not discuss a little bit about that? And if you have questions at the end of the session, we'll have some occasion to talk about that. I want to stress you that, the .NET framework is going. I mean, it's not going in the sense that they will drop the support or things like that. No, please. It will be supported for such a long time, but we have the very good news that every workload now is supported on .NET Core, and we should think about moving on in our software and begin adopting the new stuff. And this is very important because the new feature languages, new features that we have in the language in C# 8, for example, cannot be used in the .NET framework anymore. And so, if we want to leverage the best that the team is going to give us, we have to adopt .NET Core now. And the span of T and memory of T provides us a lot of many performance advantages that we can leverage only on .NET Core. So this is really a topic very hot. There is an alternate library that provides a kind of slow version of span and memory of T available on NuGet so that you can use it in .NET Framework. But of course, all the advantages are mostly if you adopt .NET Core. So this is very relevant if you are going to use .NET Core. So I am Raffaele. For people not knowing me, I am an MVP, a long-dated MVP. I mean, 16 years is really a huge amount of time. And I had the pleasure to meet a lot of people in Microsoft discussing during the MVP Summit. That is the best occasion to talk with the people like the CLR team, like Ego and other guys, discussing things and brainstorming about what's the possible future for language features, for CLR features, for security features. It's really incredibly useful for me and from my communities, because I'm kind of adopted from many communities. I talk in different countries, in different cities, and it's a great pleasure to be here again. And I mean, I travel a lot, and I have to thank to my wife for this. Okay. So the agenda is talking about these new APIs. We have very cool stuff to talk about. Mainly about the revolution that happened over C# 7 and now also C# 8, with the ability to take the reference, to play with the references even with value types. That's cool. The battery is gone. And we'll play a little bit with our new best friends, the span of T and memory of T. We will see specifically what means using them also in the unsafe world, which is extremely important because it helps us to keep the things safe even if we are dealing with unmanaged memory. That's very cool. We will see also some new allocation APIs, so the ability to allocate memory in a different way that we use it to do. And finally, the pipelines. That is, in my opinion, a very good way to experiment all the things that we have in the agenda. So let's talk about a bit about the details. Sorry, I know that the Russian guys are very strong in all the details, but I had to introduce a little bit what are we talking about. So this is extremely important because, I mean, maybe not so many experienced developers knows exactly what the difference is between value types and reference types. And I know that you probably knows because, I mean, you are developers. But it historically is a kind of important because C++ is a value type language. And in the past also VB was a value type language. And this means that basically every time you pass something, you copy. And you copy things, and you copy things. And if we look at the history, VB6 was the very first language that changed the strategy, switching from VB5 to VB6, from being a value type language to a reference type language. And this dramatically improved the performance of the language. And it's a kind of lesson learned from the language designers that said, oh my God, we can really get a lot of performance kind of free, and it's not free, of course, but simply changing this stuff. And when the .NET started at the very beginning, had to choose between the value type language, let's say the type system should be modeled as a value type language or a reference type. And the answer was, what if we split the type system in two and we decide that certain types are value and other types are references? And that was the correct choice after all, because we had most of the benefit of the two. The historical problem in .NET was that we didn't have much tools to play with the value types. That's the problem. So every time we deal with the structs that are value types, the most complex value types, we don't have enough powerful tools in the language to deal with them in order to avoid copying, to instruct the compiler to do the right thing for us, and so on. And all these tools are a lot of things. I mean, there is a huge list that has been implemented in C#7 with the ref all things that we have seen in C#7.0, 7.1, 7.2, 7.3, and now the latest are coming with are now available with C#8. So it's definitely a revolution because we finally have the true parity between the value types and the reference types. We now have the ability to play with both. And I mean, even C++ had a similar glitch because they historically had copy constructors in which you can decide what to do when the type is passed by value and you want to copy the class, the object. But you didn't have the occasion to optimize this. And this came in C++ 11 with the move constructor, which basically means I give you the ownership of a value type, so you are dealing with a kind of reference, right? And if I give you the ownership, I will avoid the copy, and that's done. And that's the very important point. So, the point is, use less GC so that we can improve our performance and avoid making, stressing the garbage collector. That's an important point. Which looks like the garbage collector is responsible for all the bad things that happens in our applications. That's not true, of course. The garbage collector is a good friend for us. But we want to avoid let's say, an excess of work due to our laziness in designing the application helping him in a different way. And so basically we are saying, what if we play a little bit more with references but applied to value types? And so every time we have some values, we want to take the reference and play with references instead of the values itself, so that it does not get a copy that is a performance hit. We know that copying memory is a performance hit. So basically, it came to this new idea of declaring a strange type of structs, the ref structs. The ref structs, it's a kind of guarantee, because historically the structs can have value types, but can contain some fields that must be managed by the garbage collector. And so you don't have any guarantees that this will give you something that will not stress the garbage collector at all. How can I have this guarantee from the compiler that I will not hit the GC? I wanted to have a guarantee. I want to my compiler stress me as soon as I do something that potentially is a performance hit. That's the point. And this is true with the ref struct. The ref struct is a value type that can only live on the stack. And I have no way to circumvent, because the compiler is checking for you and is telling, hey guy, you know, you cannot do it. You cannot do this declaration, because otherwise it will be taken from the garbage collector. And the second important thing that happens is that I don't want either risk that the allocation that I'm managing disappear while I'm working with the struct. Because otherwise we would have something that is unsafe. I mean, unsafe in the bad sense, in the sense of crashing. Because when I'm playing with some memory and this get deallocated in some way and disappear, of course, that's super bad. So when we have a span of T, but it can be also your custom type. I mean, you can invent a new type that mimes do similar things to span of T. Span of T is just ready to use and is very it's very handy to use. That's the point. But basically, the ref struct gives you a view to the memory. So you must think to the ability to view some memory that you don't own. So you don't have the reference in the sense that you have the ownership of the memory that you are viewing. You just view it, and you cannot do anything on, in the sense you cannot manage its life cycle. And when you declare the read-only structs, ref read-only structs, it means simply that are ref structs, so they live on the stack. They are read-only in the sense that you will not modify the reference that they hold. But they don't hold anything else, because if you look at the sources, you don't have anything in there. They didn't manage to allocate anything. They simply capture this small allocation that give you the opportunity to view at the memory, and nothing more. Okay? When you take a span of T, basically you are viewing something that is really from this allocation, and this will totally disappear with the bracket closes. Okay, so you don't have when the brace will close at the end of this piece of code, of this snippet, everything will disappear, and the garbage collector will never have any hit. Okay, so the most important thing is that you don't have to do any special construct. So you can view as you always had, and take simply this span of t, and you will get this view, and is of course free. Of course, the new will be held from the garbage collector because it's a new. But the point is that the ref struct, so your span of t, will not go there. You will just observe the memory that has been allocated from someone else. And you have its counterpart, that is the read-only span. That is important because, for example, the strings are read-only, and you don't have anything that you can do to modify the string. You can just observe it. You can read it multiple times, but you cannot change anything inside the string. And that's super important because, of course, you can mess it up everything because strings can be reused by several points in the application. And in this case, the read-only char points to this hello world, and you can slice it. And this slice operation is extremely important, and you can do it both on the read-only span or even in the span of t. And you will obtain just a view on a smaller part of the memory. The important thing is that you don't have to worry anymore about the index and the range that you are dealing with, because the slice gives you apparently a new array, but it's not. It's just a view on the previous one. And so you don't own the memory. You just get a view on a different interval, on a different range. And the result is, in memory, of course, is the one that you can imagine. One very popular example is the trim operation, which removes certain characters from the beginning and the end of the string. So we take a read-only char, read-only span of char as a source. And by the way, it gets converted from a string automatically because you can get the conversion for free. And this is, let's say, the algorithm to remove the spaces and from the string at the beginning and the end. But the cool thing is that we don't need to reallocate anything. We don't need to copy the content of the trimmed string in any other place. We just have a view without the spaces at the beginning and the end. So we are just looking at the part of the string that is in the middle of the spaces at the beginning and the end. So we are just changing the view to a string. And by the way, it's strange because historically things happen in very different languages, and C++ recently introduced a string view as well, which is a view on a string. Just because this is a common problem. This is not something that only hits the languages that have the garbage collector. It happens everywhere because you simply don't want to mess it up your application by copying multiple times things or lose time in creating new objects. And what you obtain is of course a read-only span of char, and it's not a string. And this is a problem because if your application is not ready to deal with the span and the read-only span, of course you cannot do anything else. So at the end, the receiver of this of the producer of the read-only span of char in your application will not be able to do anything if you don't modify the application in order to use the read-only span of char instead of a string. So you have to think about what are the hot paths in terms of memory, of course, in your application, and begin thinking, what if I want to reduce the amount of strings that gets allocated or not? For example, nowadays in .NET Core 3, we have the new diagnostic tools that are shipped by Microsoft as global tools. And you can install with .NET install -G and so on, which is very popular because it resembles the npm install -G, okay? And you can install the agnostic tools and see exactly what's happening there. And you can collect the data from a dump and freeze your application in a certain moment. And then you can analyze the dump by command line with the SOS without a WinDBG at all. And this is a very important, because if you try to dump all the strings that in that moment that you dump it from your process, and you see how many strings you have in your application, you will discover that you are doing it wrong. I mean, probably it's very easy. I mean, if you didn't optimize before, you will discover that strings are destroying your application. And you can probably optimize something. How can you do that? So what is the practical solution? Adopting a span of char instead of a string wherever is possible. Of course, it's not possible everywhere, especially when you have libraries and you have to begin passing strings. You have to think about and saying, what if I don't allocate a new string now in the trim, but I replace with my utility that is this one, and I take the trim of the string and I pass the read-only span of char at the upper level of the application. And maybe my consumer of the trimmed string is able to analyze the string without requiring duplication. If you manage to do that, you substantially have less strings in your application, and your memory consumption is less, the garbage collector is going to hit less, and of course, the performance is better. So this is the procedure. There are limitations, and this is why I want you to understand very well what happens when you begin playing with span of T, because you may exit this door and say, okay, I will replace every single string with the read-only span of char, and you will be deluded very, very soon, because there are problems, and since this must live on the stack, you will discover very soon that you cannot put this a field that is a read-only span of T as a field in your class, for example. You cannot do it, because otherwise it will go to the garbage collector again, and so it won't work. So there are limitations. The good part is that the compiler is simply advising you that you cannot do it, because otherwise you lose the advantages. That's the main part. So this is the most important part. But on the other side, you know that if you happen to be successful in this, and you can manage some local string, and you have some functions that returns read-only span of char, and you can manage to extract information or analyze the text this way. If you have, for example, a parser, it will be a common example for this. You will be successful. Another limitation is that if you have a function that has some kind of asynchronous behavior, you cannot declare here a span, because you know that the machinery of C# totally rework the functions with the state machine in order to satisfy the asynchronous requirement. In order to avoid this problem, you can simply use the local function. And the local function is able to return the ref, and so you will be successful in overcome the limitation. So this is a good usage of the static of the local function. That now with C#8 can be also static local functions, with the advantage that they cannot capture locals, and so it's the code is more clean, basically. And here you have a good example, in my opinion. But if you try to declare the span of byte this way in a class, you will get lost immediately. You can do this, you can have a field of type span, but only inside another ref struct. It's a kind of popping up all the ref structs at the upper level, like we did with async await. Okay, it's a similar trick. And since you can't play too much with the span of t, you will end up in saying, okay, I cannot convert anything to an abstract, of course, because also the stack is limited. You cannot play too much with huge things there. I need something that really keep the ownership of the memory that I allocated before, and then give me also the advantage to play with slicing at a lower cost. So how can I do this? And this is memory of t, which is just a read-only struct. It is not a ref read-only struct. Okay, that does not have the ref one. The ref is the guy who is giving you the limitation. Memory T is the type that gives you the ownership. So it takes the amount of memory is held by a reference, and he takes the ownership of the reference. And you know that, okay, he will take something that will be managed by the GC, of course. Like in the previous example, the new is, of course, in charge of the GC, but he takes the ownership, so he can be used as a field in a class, and whatever you want is very handy. And the advantage is that you already have all the methods, and the advantage is to obtain easily a span of t from a memory of t, and you can slice memory as well in this way. It depends from, what you're going to need there. Now, if we compare the string trim, so the classical one, the one in the BCL, and the trim that we got from the example of the Microsoft documentation, because it's a sample code, we see that there is a clear advantage in reusing, in using the span family of APIs, because we don't produce any more strings, we don't have allocations at all, which is the primary thing. And so benchmark.net tells us clearly that you have advantages that mostly come from the work that the garbage collector did. When we come to the unsafe world, the things becomes even more interesting, because in the unsafe world we know that we kind of enter in a room where everything can happen. As soon as we declare a method that is unsafe, we risk to mess it up at the entire safety of the application. And nowadays that we have to develop software faster and faster, having guarantees that everything goes well is fundamental. So how can we minimize the risk to do something very bad with the unsafe code? And span of t is very cool because given some pointer that we obtained from some C++ code, it doesn't matter what, how can we manage this unmanaged allocation in .NET, in C#? And the answer is I can build a span of byte around this pointer, which is unsafe. But the span of t will guarantee us that we can freely work with the span of byte without risking anything. The premises are two. This is a good pointer, and this is the correct size. If we did the computation right at the beginning, from now on we can use a span byte without risking to do anything wrong. Because when you have a pointer, a raw pointer, we know that if we exceed in writing after the pointer effective allocation, of course we risk to overwrite something else, and the application will crash. But And more importantly, there can be some security bugs, of course, because the old buffer overrun is something that can hit very hard many applications. So from the security perspective, this is an aspect extremely interesting. But once we have the span of byte, we have the safety that with the checks that if we exceed the boundaries, we will receive a managed exception, which is totally different. And we can also play with the correct cast. And so we have just one structure of type wave header. This is the pointer at the beginning, and the length is 1 because he knows that it goes multiplied by the size of a wave header. And if you are familiar with the C computation of the size, this is not a surprise. I mean, it's the way the native languages work. And so we substantially realized that they are not an old dream, so the ability to cast something to a totally different type without having to do very nasty thing in .NET. So in the past, if you had to write, let's say, an application that deals with the DNS network response. The DNS network response is the classical example that can be solved using unions in C, because the size of the answers are very different, the size is different every time. And so it's difficult to match with the, let's say, .NET version 6, because every time that is something that is dynamic, you cannot simply cast something dynamically right after. It's extremely complicated. So this is an example where we can, frankly, play well, in the sense we have good tools to manage that and without losing the safety. So it's a big win. We also have other interesting tools that are a bit less known, but extremely good. And I have to say, be very careful when you use that, because memory marshal and unsafe classes, those two helper classes, can lead to application crashes, of course. You are saying the framework, okay, please trust me. I know that the allocation is not made of bytes, is made of WAV headers, and so I want to cast this allocation to this type. It's you can trust me, and he will do it. It's very powerful, but also very risky. So you have to be very comfortable with what you are doing. Or you can materialize an instance of this starting from an application, from a bunch of memory that is not that is native, that is not managed, which is super interesting. I mean, in the past you could not do it. Even the same as with unsafe read, and have substantially a similar behavior. And you can even avoid the materialization, so no new memory, no nothing new, but just getting a reference to an unmanaged portion of memory, but you want to see casted with a specific type. Which is a big win, because if you have something that comes from a DTO, let's say, that comes directly from a socket, and you know that it's large enough, the buffer, and you know that it's that type, and you don't want to copy that or deserialize in binary or something else. You just know that you can cast the unmanaged memory, and you have the information you have. That's super fast, because at the very end, you have a single instruction in a year. It's super fast. So this is the best way to obtain a reference to something that you know is the correct type, and you want to deal with it. we are talking about value types, okay? Not classes, they're totally different thing. So, I will make some, I will show some code later on. Let me first lose my voice and then we will take a little overview on the memory allocation APIs. Okay, we know this stuff. New bytes, we know that the garbage collector will take care of that. We know that memory of byte will take the ownership of the reference. So it's pretty simple. We don't have anything special here. There is something that, I mean, we should stress that is always valid from a long time, because the stack unlock on the stack, and we can leverage this if the allocation is small, because the stack is not that big, okay? And we have a very small. This small buffer is useful for a small amount of time, and we know that we can do something, copy and reuse and make some calculation and throw it away. Why not using the stack? Okay, it's like adding something to the ESP in assembly code. You know? So we reserve some space in stack in C++, and then we say, oh, I want to have some free space to do my nested things and my temporary buffers, and then I will throw it away right at the end. Another way is to use the array pool. The array pool is very handy because it gives you the opportunity to reuse certain amount of memory. And you have to be very careful, because once you rent and you express the desire to have a certain size, let's say 10,000 bytes, you will probably not obtain 10,000 bytes. You will obtain one page, or maybe the immediate approximation is 10K, but it will be maybe equal if you're lucky, but most of the time is greater than. So you have to be very careful, because we are used to use the length of the buffer as a parameter as an input to many functions. So we always say, let's new a blob. And then when I have to play with the blob, I say, oh, the length is blob.length. And it's wrong, because in this case, my allocation is bigger, and so the length of the blob in this case is larger, because the size is the one that I required was smaller, and I obtained a larger buffer. So I have to be very careful. In order to avoid this, the best thing is to obtain a span over the allocation obtained here. So you basically have to rent the pool, and immediately after take a span of t over the rented buffer, so that you obtain the rent amount of your view will be exactly of size. Because I request size, I obtain size plus 10, and I don't want to use size plus 10 as a parameter. I want my parameter is a size, because I want to use just that memory and not more. And so in order to restrict the view, I want to create a span of byte that give me the view over the first portion, the one that I really need. And so you have also to play nice, returning to the pool the amount of memory that you don't need anymore. So it's up to you, it's your responsibility. You rent something, and you will return somehow, somewhere, who knows. But it's your responsibility. This is a good API when you don't have exactly defined the life cycle of your allocations, which is never a good thing, by the way. Because defining the life cycle is one of the first principles in an application. But sometimes it depends from external events. It depends from something that you don't have control on too. And so the best thing in this case is, okay, I want to leverage an array pool, and then maybe I can have also my own directory, let's say, of allocations, so that I don't mess it up everything, I don't have leaks in the sense. And instead of the standard pool, we can also create our own pools. And you can investigate if you have very special needs in your application, the size of the pool and how much you want to play with. Then we have the memory pool. And the memory pool exposes the iDisposable. And this is very handy because when you happen to close the brace, the memory will go away. It's neat. I love this kind of pattern because it's very clear. And with the C#8, you know that you can totally omit the braces, and you can put the semicolon there and say, okay, this is my declaration, and the memory will go away at the first closed brace of the method. Okay? It's a new thing in C#8. I invite you to take a look at the feature, because it's nice because you avoid the so-called triangle when you have multiple using one inside the other, and you have this indentation that it's nasty. I mean, we don't. We know that many developers really take care about, I mean, the aesthetic of the code. And when something is not good to see, I mean, screw it up. And you have this kind of two guys, the one that is pure aesthetic, the other is pure functional, and it looks only at the optimization perspective. And when they live in the same team, and the application crashes in pure craziness. The memory pool is similar, but supports the disposable pattern, and so you can rent the size. You have to be very careful again, because the size, this is wrong. It's not equal. It's greater than and or equal. Okay? Most of the time, this is got from an example. I was going to demonstrate that if you use a weird number to allocate, of course, it will never be equal, because it usually is a kind of a page of the pool. So unless it's a power of 2, of course it will be different. And then you can do whatever you want. You can slice. You can take a span of t. You can do whatever you prefer. And again, you can create a custom pool by deriving memory pool of t. It's up to you to choose the one you prefer. I am not aware of special advantages, if not architectural. Another important thing is that you can omit the unsafe keyword at all when allocating on the stack if you use span of t. So this line does not require unsafe anymore. But because after all, I mean, it's very clear, the intent. The span of t will go away at the end of the method. And the stack unlock will go away at the end of the method. So the only thing that you can do to mess up everything is to specify here a huge amount of bytes that is so close to the stack allocation size, the maximum allowed, that probably will crash as soon as you do whatever else. So this is the only way in which you can mess up everything. But otherwise, this is perfectly safe. So there is no reason to declare this line as unsafe. So be careful about the size of the stack, of course. And this is by design the default, the best method, the fastest way that we cannot allocate any memory. I had no code review with Angular, and so I know that later on he will screw up with me about all the details, but I am quite confident that this is correct. Another one that is very interesting, and is super interesting especially for the types that we will see in a moment, is read-only sequence. Read-only sequence is not to complicate your life. The problem is that this is the real use case. It's all the previous allocation method assume that you have a continuous memory available, which is totally false in case you are communicating on a network stack, or if you are downloading something from a device and from the IoT, and so on. Because data arrives in chunk. For example, I showed in St. Petersburg during .next, which is available on video, by the way, an application that runs on the Raspberry Pi on .NET Core, and have to split the frames, the video frames, in real time in order to give part of these frames to the browser and another part to the OpenCV library in order to recognize the face. Okay? And in order to process in real time this stuff, of course, I have to deal with chunks. And the first thing that happened to me is okay, I can analyze, I can take span over the chunk of memory that arrives. But if the chunk is too small, because the H.264 encoder is giving me pieces of memory, I have to create a copy and give me this piece of copy, and I have to copy in a larger buffer in order to obtain exactly one frame. And I need one frame at a time. But in the case of the network stack, in the network stack, the problem is that they rewrote everything from scratch, and so with Kestrel, now I have a better memory management, you have a better way to communicate that has improved version after version. And so in order to optimize the memory allocation and to minimize the copy, they created this model. By the way, if you need to, for other reasons, you can reuse, but you will see that most of this is available just in the system I/O pipelines. So this is very specific. And the only sequence is a linked list, because usually you receive from the communication stack, from the network stack, many chunks of memory. And so the API tells you, okay, you get this first chunk that is contiguous, and then another chunk which is contiguous, but the two are not continuous, of course, because you received them in different moments. So the timeline is different. You maybe have some kind of delay in the network stack, and so you have different allocations. And this is a read-only sequence. So it's a sequence, a list of read-only sequence segment of T, which are usually bytes. The problem is that the API was really kind of internal. It's public, you can use it, but it's kind of internal because it does not exist any concrete public implementation of the read-only sequence segment of T. So you can easily create your own. You can look at the sources on GitHub and understand how it works. Very super easy, nothing terrible. But it's not something that was thought for public consumption. So it's something that you need to understand in order to use the pipeline, but it's not something that really was meant for that. And so we are at the pipeline API. And you can wonder why I put it all together, the span of T, the memory API, and then the pipeline, because they are kind of a consequence of one of the other. So when you deal with the span of T and memory of T, you have to think about the memory, and all the API that we have seen before are useful to understand, are mandatory to understand the pipeline API. The pipeline API is a kind of modern API for streams. So if you have a system IO stream, okay, it is a good candidate is to replace the usage of the stream with the pipeline. I mean, not always, not all the streams should be replaced with the pipeline. The stream is fine. I mean, you can play with it without any problem. But if you believe that producing and reading is kind of difficult work because you don't know how long is a stream, you have multiple concurrent read, and you don't know when the producer will stop producing a stream, and so on. Basically, these cases are dramatically simplified by the pipeline API. And basically, it's a first in, first out structure, and there is a very good decoupling between the readers and the writers. This is very good because we need to keep separate the role of the application who read and the application and the part of the application who writes. Okay. It provides a built-in memory management of buffers. If you want, you can overcome a few things. And leverages, of course, the power of all the things that we mentioned before. The readers may decide to consume only a portion. This is super interesting. So if you, as a reader, want to use a piece of the memory that comes from, let's say, the H.264 streaming video of the Raspberry Pi, and you discover that you just identified the end of the buffer and say, okay, I don't want to read anything else, and I want to close the sync because I don't want to take everything. I just want to take the thing that I want. And the next frame, I will be more than happy to read all the rest. This is a common situation, if you think, especially in streaming. But it's extremely difficult to make it with the streams, because once you begin reading, you have to provide a kind of buffer to accumulate things, and you cannot stop doing it. And this is a common problem. And with the pipes, you can just read a portion of the memory, and you are done. Okay, the other problem that I found a lot of difficulties with the pipelines. And so it's let's say what most of the slide is about the pros, and the only cons that I had is that having a pipeline that can just consume byte is a problem if you use for different purposes. So for example, if you want to consume something that you read from a stream that is structured as a block of chunks that you can identify the structure that has, like headers and records in the old style programming. You read something from a disk and you know that the first part is a header, and then you have multiple records of a fixed length and you want to read them over and over. You cannot just specify, I want a pipeline of my type. You just have bytes. So you have to make the computation about the size by yourself and manage all the stuff and convert back and forth with your code. So the first part is, how can I write a pipe? And writing a pipe meaning pushing things inside a pipe, because a pipe is a pipe, and I want to push something in and then read. By the way, you can even begin reading, because everything is asynchronous, and once the pipe exists, you can start reading. You will not get anything, of course, because it's asynchronous, it will just wait. And so reading before writing is fine. Okay? And in order to write, you have two kind of strategies. The first is I want to reserve some memory from the pipe, so he will take care of to allocate the memory you need, at least of main sites. He will reuse the pools that we mentioned before. And then we say, okay, I want you to put the bytes for the string message inside the span that I obtained from the memory that I obtained before. So I asked some memory to the pipe writer, and then I want to write something there. And I can simply, in the get bytes, telling the get bytes, put the UTF-8 bytes in this allocation that was provided by the pipe itself. It's a good way to proceed. At this point, the pipe doesn't know how many bytes you have written there. So you have to provide the number of bytes that you actually wrote. That's the main point. And so you have to say advance. And since it's like a cursor, no? And you say, I wrote like 56 bytes. Okay, I will take this one. You can write whatever you want inside that memory. Doesn't matter. The most important thing is that you want to advance these sites. Okay? You can play with the buffer whatever you want. You can write it all. Doesn't matter. But the only part that will be seen by the pipe is the one that you signaled with advance. And at the end, in order to commit, let's say, to make the reader know that something is available, you have to flush, which is not the string flush. It's totally different. It's something like, I want to advise you that something has been is available now. That's it. It doesn't provoke anything else. And when the pipe completed writing and doesn't have anything else, you don't have anything more to write, you can complete it and say, okay, on my side I want to close the pipe because I will not push anything else. And so this is just to say, I'm done. Let's see the other strategy. And the usage depends on you. I mean, they are equivalent. You create the pipe again. You can let the get bytes allocate the memory for you in the old style. If we go to see, this is slightly less efficient because we are not reusing any pool of memory. So this will hit the GC a bit more because it's a normal allocation of the GC is not a pool. Okay? Unless you decide that your operation, like get bytes, hits just your own memory pool, and also, it's fine. And, okay, no, Sophia, you're in the right bed. I will not come. Let me conceal the message. Yeah, it's been fun. And at this time, we have the pipe writer write as async that can complete the operation. So you don't need an advance, you don't need flash async, because with the write async, you have everything. It's automatic. You don't have to provide any other information. You are specifying exactly what you want. In the previous case, we have an allocation that was provided by the pipe itself, and it could not. The pipe could not know what to do. But in this case, it knows. Let's see reading, and then I will show briefly some codes so that you can have something more interesting. Also reading the pipe can be both asynchronous, which is of course the best way in order not to block any thread. And in the first case, you have an infinite loop, like a while true or something, and where you can await the reader's async. And you can start reading far before than any write occurs. So if you have a dedicated thread, for example, you can just begin reading, and you loop and loop and loop, and that's it. And as soon as everything is done, the result is concealed or buffer is empty, you can exit, because it means there is nothing more to read and you are done with everything. And when you want the buffer, you just get result.buffer and you play with it. In the synchronous strategies, you simply say, oh, I want to see if something is available. So try it. If something is available now, I will use it. If it's not available now, I don't care. I have other things to do. It's a kind of polling. No, I continuously ask if there is something to do. Again, it's up to you to decide what is better in your use case. So, let me switch briefly to the example. So the first example I want to show you is, this is the part of the demo from the streaming, and you can see that you can do it. I mean, find sequence is a magic sequence that is passed as a parameter here, that you have to find inside this read-only span of byte. And this basically is a magic sequence that is part of the H.264 specification, as it marks the end of a frame. It's not a fixed sequence. It depends from the resolution. It depends from many things. But anyway, this is, I mean, the algorithm per se is not really interesting. I mean, it's something that just search something here. The good part is that I don't need to make any other copies. I don't need to split, or I don't need to process anything else. And when I find the correct match, simply slicing and so on, I really have to return the offset that I found. That's basically the trick. Another more interesting example is this application that I call it master. What is that? I mean, this is very super simple. I have a photo on my disk, and I read the photo for reading, and I just copy it on the standard output. Super simple, nothing more. It's a binary, okay, output, so you know that console out can support the binary output. That's it. And so I want to see what can I do to copy from another process the content that has been pushed out from the standard output. And so the slave is basically saying, I want the ability to run the master program, of course, because I want to run it on demand. I take the exe full path. And I want to process the standard output and process this file in here. What does it mean? I mean that there is this wrapper around the process start, okay, just to make the output go. I have this source file, so it runs the process basically. It captures the output from the process that has started. Okay, it takes the stream, and he wants to use the stream. How can I capture it? So let's see the execute async before. The execute async basically prepare the process, and when the process is started, then use a binary reader in order to capture the base stream, which is the standard output of the master program. and delegate this standard output processor, this lambda, to do whatever he wants with the stream. So basically, what I am doing here is I create a new file, a local file, which will hold the copy of the image. I prepare the reader of the pipe, and you see I created an empty pipe here, very simple. And I say, as soon as you read something, copy this stuff on the target stream, okay, which is the create. And this copy to async is not something that exists in the BCL. It's something that I wrote, and I will show you in a minute. And on the other side, I have the writer. And the writer is something that takes the stream and push it in the pipe. So basically, I have something that brings streams and put in the pipe, and the other part takes the pipe and put in the stream. Of course, for a file copy is useless, but just to show how it can be used, because you can do other things with the pipe that we'll show you in a second. And once you have this, you can take the stream and copy to async to the pipe writer, which is exactly the push. Since these two are asynchronous operations and they return a task, I want to stop only when both are closing. So when they completed their work, I can end my process standard output. And basically it means that if I go to, if I go to the folder here and I delete this result and then I run this slave again, okay, we will see in a moment happening the copy again. We will see copy finish and dispose in the process, okay? And we have the copy of the photo that I shot yesterday in the center of the city. Beautiful city. You recognize the decorations, I know. That's it. And this is pretty much useless, of course, because you copy a stream to a stream at the very end. I have just added a pipe in the middle. So what's the use? The use is that you can even do very many other things. So the idea is that I can just use it to copy the content. I can add in the middle another block that is a no operation block that just do nothing, intercept, or I can create another one that is a logger and so on. So think about for a minute that we have a pipe that is the source, kind of block that is reading something. And then you want to compose the pipes one after the other, like it was Lego bricks. And then you have a final block that is the one that writes on the file server. And in the middle, maybe you want to apply a transform to a file. You may recognize that is an image. And if it's an image, you can transform the bytes of the image and change the file format. And brings a JPEG and push on the other side a PNG. And so on. And you can continue this kind of transformation, and which is extremely useful. The problem is that the pipeline API was not designed to do this kind of transformation, so the blocks are a bit more complicated. But if you want to, I invite you to take a look on this, and I will leave for you the sources in a repository I created on purpose for this meetup. So you will get, of course, the slides, but also the code for the things that I created on this. One of the most important part is that you can also split the pipe. So I designed this strange idea of saying, what if I want to process this file that I read on multiple pipes, and I want to duplicate. So I can basically create a one-to-many block and say I want to split and distribute all the bytes to several other pipes. And then on the other side, when I wanted to join, I have also the many-to-one that can be, for example, the sum or the average or whatever you want. It's kind of aggregation, very similar to what you can do with data from a database or whatever else. So it's very interesting to use. You see pipeline utilities broadcast, and you have all the stuff in here. The copy to async that we have seen before are here. For example, this is the reading part, and we have a stream that is entering and then reading the stream, and then we book some memory, and we read the async the stream, and we write and advance the pipe. And you see that this is going on and on and on. And on the other side, we have the same copy to async, but taking the pipe reader. So it's the one that pull out the bytes from the pipe reader. And again, there is a while true with the read async from the pipe reader, and we can break everything finished. We process. These are the segments that we mentioned before in the allocation. So when you read from the pipe, you get this read-only sequence of bytes, and the memory chunk are read-only memory. So you process chunk by chunk this stuff. But you can ask the pipe to give you also only one big piece of memory without splitting in chunks. This is one of the options when you build a pipe. My voice is going, and I believe you may have some questions, so I want to briefly switch to the last slide that is kind of, yes, this one. And so basically try to move to the new tools, to the new API, and then experiment something. I don't want to say blah 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 about this. We talked for a long time up to all the thing, and I see someone want to put some question. Thank you everybody for your time and having me here again. I hope you enjoyed the session, and thanks. Okay. Yeah. While you pass the mic to the guy, I will show the repository.
Raffaele, thank you a lot for your presentation. Could you explain, please, am I right about with pipes we can build some kind of interceptor pattern? So we can put additional job at runtime using pipes.
Of course. I mean, pipes are for moving data, basically. So you have you read something like a stream of bytes that is flowing. Think about a network. It was created to optimize Kestrel. So ASP.NET Core, the core part. So it's an API designed to bring something from a source. It doesn't matter if it's the network or anything else, and then moving this stuff around until you want to consume from somewhere. So yes, you can put, as I was explaining before, like a log block that I briefly showed for a second, that can intercept the flow and process it to do anything else.
It could be intercepted because of it is a struct. Because we can see a memory chunk.
Well, it's an implementation specific. I mean, I designed the piece. The pipe per se is not possible to intercept adding something. I cannot say, hey, I have this pipe, I want to add an interceptor and get and spill some data away. I designed those blocks in order to achieve this kind of purpose. And I say, what if instead of a single pipe, we chain multiple pipes, and we minimizing, of course, the amount of copies that may be needed in order to flow the memory around. That's the basic idea.
Thank you. My question is it possible in the future we will use pipes instead of streams everywhere?
Probably yes. Of course, depends on the producer and the consumer. If you take Kestrel, for example, with the latest release in 3.0, they managed to give you the opportunity to have both the stream and the pipe. So you can consume the one you prefer. Of course, they didn't remove the streams. They offered, as an addition, also the pipes, so that if you want to attach to the network stream coming from Kestrel and to consume some data that is flowing to you, you can do it. For example, a file download or a file upload, and you want to write your own implementation for the uploader, and you receive this data from the browser and you want to consume it. You now have the ability to bring directly from the pipe the Kestrel offers to you.
You have some kind of a pipe of people with those questions.
Thank you so much for your performance. I have one conclusion from your speech, and I just want to ask you to approve or correct me if I'm wrong. So before all this unsafe stuff wasn't a recommended practice from Microsoft, and to be honest, I just never saw unsafe code or some raw memory access in real production code. But now we have these new instruments, debugging tools, and this span of T looks much less scary than pointer star, you know. And now all these guys who are avoiding to use unsafe memory should start their experiments, because .NET developers have some long strategy to make this work. Am I right?
Let's say if you don't abuse from unsafe code, just on the purpose of using the unsafe and say, oh, I will try this because I will do better, no? And I am smarter than the base class library, and so I go unsafe. I don't recommend this kind of approach. I recommend not to stop and say, okay, if I really am losing performance because I am copying stuff around, I can avoid extra copies by using either unsafe or other things. I mean, span of T and memory of T are not about unsafe, about memory management in general. But they are very powerful when you combine it with the unsafe code, of course. In this case, yes, I don't stop just because it's unsafe. Absolutely, yes. And this is super important, because there is a lot of code that is crappy just because they wanted to avoid the unsafe keyword. And that is wrong. I mean, the good part is that now with C# 7 and 8, you have tools to minimize the amount of code that is unsafe. This is the good news. You have APIs. When you get the pointer, the raw pointer, you put it inside the span of T, you know that from that moment on, you will not be unsafe anymore. I mean, if your premises, the length of the buffer is correct, you are safe. From now on, you are okay. But if you put unsafe at the beginning and then 1 million lines later you add your brace, oh my God, how can you find the problem? Because you were mentioning the dumps and the new diagnostic tools. But when you have an unmanaged native crash finding the responsible is extremely hard. I mean, it's not so trivial. It can be very, very nasty. With managed code, you can analyze the exceptions. You can see a lot of other things. You can see the code, the stack trace, and you understand a lot of things with the SOS. But if you go straight to native and you have this dangling pointer poking around in the memory randomly, oh my God, that's too much. So yes, if you use with your heart.
Thank you so much.
The pipe is interrupted. Anyone? I scared all the time. Okay.
Thank you for your talk.
Thank you. And I have to say, I wear my suite of the .NET, of the Moscow.NET, yes, with proud and our latest user.
Быстро копируйте скринкаст на флешку с компа.
Yeah? Okay. Okay, this is not public at the moment. I will publish very soon, and you will get the code in this repository. Okay?
Вернем.